This time. Hello, everyone. It's my pleasure to introduce our guest, our speaker, Professor Nicola De Nitti. He's visiting us from University of Pisa. He received his PhD in Germany, in University of Erlangen in 2023. And then he was a postdoctoral scientist in EPFL, right? EPFL, and now he's just obtained a track position assistant professor at the University of Pisa, and he's visiting us for several weeks and interacting with many mathematicians. And today's talk is of general nature, and he will talk about non-local traffic models. Please.
Thank you so much, and thanks for the hospitality. I'm enjoying being here. Okinawa is really a beautiful place, and this is the first one. For today, we will keep the topic a bit light. I assume there is a lot of variety in the audience. And we talk about the traffic models, in particular, non-local traffic models. We will see in which sense. But first of all, I guess we should start with what's a mathematical model anyway. So mathematical modeling seeks to represent observable phenomena, very complex, trying to capture some aspects of them that are essential for the purpose of, let's say, analysis, prediction, and regulation, let's say, intervention for the policy even. And these steps in the model are, first of all, to identify the phenomenon not to describe, then identify the variables to describe it, then according to biological, let's say, observations, physical observations, clinical principle, one should formulate the relationship between these variables. And then finally, once one has this relationship, typically in our case in the shape of a differential equation, then it's the moment to try and analyze it, to understand patterns, and then eventually make predictions using either numerical or numerical simulations. Now, of course, every model is a simplification of reality. So the famous quote by George is that all models are wrong, but some are useful. So indeed, although as this comic tries to convey that there are simplifications, and one has to account for what are the fundamental, let's say, phenomena and what are a bit disregarded at the given time, still there is some utility in mathematical modeling. And especially, we will focus on traffic flow, where the utility is clear from the point of view of our daily life. I mean, of course, we would like the urban mobility in our cities to be very efficient, without delays, moderating consumption of fuel, and so on and so forth. So clearly, traffic flow is an area which some analytical study is very much needed. I mean, one could try, of course, to study traffic flow purely from the empirical point of view, observe cars moving, and then try to make observation from this data. But some kind of modeling helps in many ways. I mean, first of all, of course, to try and reduce the complexity of the situation, try to obtain a simplified description of the dynamics that can try to preserve the essential properties of the system in order to study better. In which sense? Well, one with a mathematical model could try to isolate the mechanisms that are supposed to relate the dynamics. For example, isolate the line changes, heterogeneity in the street, road conditions, the effect of congestions, and so on and so forth. One could try to fine-tune the study of the parameters, let's say, assuming drivers are more or less aggressive in their behavior. And then, of course, the second effect is that one then should be able to carry out a critical investigation, numerical experiments, to then hopefully gain some insight to explain and predict the actual dynamics on the road. Now, our aim at the end of all of this study is, of course, given a city or a network of cities, to have efficient and sustainable mobility. In whatever sense, let's say, it is appropriate depending on also on the historical period. You see some recent developments shortly. One of the important steps when it comes to a mathematical model is, of course, as I said before, defining the variables that one would like to describe. In the case of traffic, of course, one could think about different scales of description, but this, of course, applies more broadly. In particular, one may want to consider individual vehicles and track the trajectory and the behavior of each of them. This is some kind of microscopic model. Or one could try to approach the description via kind of a kinetic approach. So they are at a mesoscopic scale, describing the distribution of vehicles, let's say using maybe position and velocity, but in an intermediate manner between the microscopic and then the macroscopic level, in which instead one just describes average densities and fluxes and so on. And we will focus in this talk on the macroscopic description, which has a long history. In fact, one of the very first macroscopic description of traffic flow inspired by fluid dynamics goes all the way back to the 50s, in particular 1955, for there were fundamental papers, one by Nicola De Nitti, the other by Richards, both of which provide a description traffic flow under suitable assumptions in a way that is quite reminiscent of descriptions of fluid flows. And indeed, all of these go under the headline of fluid dynamic descriptions of traffic. To get a bit more in detail, let us start with one-way street, and let us call rho the density of cars. Rho depending on space and time, so the density of cars at time t and position x. The key assumption derived the LWR model is a conservation principle, so that the cars don't just disappear from the street. Maybe it depends on the city, they don't disappear. Let us say that they do not disappear. So then, if we fix 2 points on this one-way street, A and B, the variation of the density of cars between these 2 points in this interval depends only on what comes in at point A and what goes out at point B at a given time. So from this, let's say, integral relation that expresses this conservation principle, one can then deduce a local differential relationship, that is this partial differential equation over there, where F is indeed the flux, so of the cars. Typically, we should assume that it is given by speed and density, of course. The speed to be determined in the sense that it is a key question in formulating the model to figure out how to describe the speed of the cars. So this was under the name of the fundamental diagram of traffic flow. That is the diagram that gives the relationship between the flux, that is then speed times density, and the density of the cars themselves. This is not a unique assumption, let's say, that the velocity should depend only on the density. But in many ways, it is a reasonable one. And the question then becomes how to figure out an appropriate relationship between the speed and the car density. Well, there are many ways. This is in a manner of speaking, an inverse problem from your point of view. But more concretely, one can try to figure out an appropriate relationship by empirical observation. And in fact, this goes all the way back to the 30s. This is a historical picture of Greenshield's making actual observation in 1933 of traffic flow to try and deduce the relationship between the density of cars and their speed. This is taken from this paper. And, well, this actually is one of the most popular models, the Greenshield's model, in which the velocity of cars is just given by, it is in a linear relationship to the car density. That is given by the maximal velocity allowed, for example, by the street, times 1 minus rho normalized by the the maximal density allowed by the street. So this is a very simple relationship, and a fine one. And the corresponding flux is just a parabola, so a quadratic flux. This is one example, but still it highlights some fundamental properties that are quite desirable to traffic modeling. That is, the velocity should be increasing reasonably, in the sense that the higher the density of the cars, the slower they should move. Of course, from the observation.
So let me make sure F rho is rho times V of rho.
Yes.
Okay.
And the other property that emerges from this observation, which is also quite reasonable, is that the flux function in total is a concave function. And indeed, I mean, these are properties that are common to several other models that are typically used in the description of traffic flow. There are many here. I just highlight a few: Greenberg's model, Underwood's model, a generalization of wheel shields in which there is a power added here, the so-called California model, and so on and so forth. There are many models. And then again, I emphasize that it is also a currently studied type of inverse problem, given traffic observation, to use the fundamental diagram. But for the sake of this talk, we will focus on wheel shields model for simplicity, and that will give us already plenty of material to study. So now that we have our description, our model, our differential equations, we would like to carry on with our program, let's say, of mathematical modeling, that is, study the properties of these differential equations. And this cluster equation that we wrote before, so let's say equations, first order partial differential equations of this type with a nonlinearity here, go under the name of scalar conservation laws. Conservation laws, because of course they came from the assumption of conservation mass, scalar, because they were focusing on just one scalar equation. Then we will consider generalizations later on. What are some key properties of these type of equations? Well, under reasonable assumptions on the velocity, which is the case for the models that we consider, finite field propagation is the first property, which indeed highlights a phenomenon that we observe, of course, in the sense that cars move with finite speed in reality. They don't just instantaneously go from one place to the other. The second property of this model is that allows for a maximum principle. That is, if we start with the initial density of cars between, let's say, 0, the road being empty, and a maximal density, rho max, that is bumper to bumper, completely stacked traffic, then the density at a later time t will also satisfy these bounds, so between 0 and the maximal density. This property, depending on the situation that one would like to model, may or may not be reasonable, but it is a classical property for this type of equations. And crucially, the third property that we'd like to emphasize is that for scalar conservation laws, singularities, that is, shocks, that is, discontinuities in the solution, may arise in flat time, even starting from very smooth initial data. So this is the typical picture. Even if one starts with a very smooth initial profile, then since higher densities move with slower speed, this profile is deformed over time, and eventually it leads to the formation here of a shock, of a discontinuity. This is a crucial property of this type of nonlinear first-order equations. And then it leads us mathematically to study not classical solutions, that is, not classical derivatives, but rather weak solutions in which the derivatives are to be interpreted in a distributional sense. It also creates one more problem, in the sense that weak solutions for this type of equations in general are not unique. But of course, for the sake of traffic description, we would like to have a unique solution starting from an initial configuration. So the question becomes, what is a physically meaningful solution that we can single out? And this is a topic that has been probably investigated. The short answer is that by imposing an empty criterion, one can select a unique, meaningful solution in some sense. meaningful in the sense that, for example, that it is dynamically stable. The center of the distributed criterion, we will not get in much detail, but it is essentially inspired by thermodynamics, by the second-law thermodynamics. So these properties are quite interesting, and this notion of singularities in particular is quite relevant for us in the sense that it highlights a property of car traffic that we all know, that is the formation of traffic jams, even starting from relatively peaceful configurations. So to be more precise, maybe I should say that even if we start with a discontinuity in the conservation law, we will have the propagation of a shock, but depending on the non-unicity of the configuration, a shock may also open into a reduction. So if the density behind, let's say, is higher than the density ahead, then this discontinuity is moved out. These are all properties of the models that are of interest for analytical investigation. Let me show you an experiment that actually took place in Japan, in Nagoya, regarding the physical relevance of this shock formation that observes mathematically. This is a famous experiment in which on a ring road that is in a periodic domain, cars, even starting equally spaced, with drivers trying to keep the same speed all the way through, still they give rise to so-called phantom traffic jams. Phantom in the sense that they seem to arise out of nowhere. So this is one example, let's say, of an occasion in which singularities are formed. But let me try to open the video, just to give you an idea. Oops. There it is. So you see, this is the picture of the experiment, sped up. You see, at some point, out of nowhere, there is a congestion forming. So you see, at some point along the road, out of nowhere, just there is this phenomenon of this kind of jam, this kind of discontinuity forming, which in principle, again, happens out of nowhere, but indeed it is consistent. Yes, it is consistent with, at least in part, with the properties that we described mathematically. So this is one instance in which really the mathematical modeling explains something about the empirical observations.
That's good.
Yes, please.
So their instruction to the driver was to keep the same distance.
Yes, although of course humans are not perfect in driving, so this is one of the empirical explanations for why still the issues arise. This, of course, is the simplest type of space.
But if you were to be able to actually keep the drivers to do what, like exactly what you told them, then that wouldn't happen, right? But in the equations, you don't consider this sort of stochastic behavior of drivers. You are.
This is the first attempt at the model, let's say. But in fact, you see, there are visualizations to account more precisely for this dynamics. So first of all, I should be basically saying that in the real model that we considered so far, indeed we have the shock formation, but these phantom traffic jams are not completely explained in the sense, mostly because of the maximum physical. So even at that level, there is some additional effort to make. So there are many generalizations that one can consider. Here I list just a few, but there are many more. So starting with second-order models, that is, by second order here we mean systems of equations. There are many. Here I cite two that are from the most famous ones, the other model from with vitamin pain, ARZ model, but again, there are many others in which introducing two equations, let's say one for the density and one, for example, for the velocity, for some kind of generalized momentum, helps uncover other phenomena. There are also models with two phases in which one tries to study simultaneously what happens in, let's say, a congested regime, and what happens in a regime with, let's say, free flow, when there is not so much density. I can consider multi-population models in which there are different types of cars, different types of vehicles. One can consider models with stochastic perturbations, indeed, models with time delay, accounting for the fact that the drivers react with a certain delay to the conditions, and so on and so forth. There are many.
I guess answering your question, I guess the driving at exactly the same speed is, I guess, an unstable fixed point usually. So if
soon as
there's
there's a
a small
perturbation,
perturbation,
it will
slip out of.
Yes.
That's usual.
Yeah, mathematically, this comes down to a question of stability for knowledge uses.
Okay, continue with another question. But so I guess it would be very different if you say, oh, the goal for the whole team is to do as many, roundabouts as possible in a given time,
Yes,
or
that's,
just keep the distance. And then one solution would be just standing still, I guess, right? One simple,
yes.
trivial solution.
That's
Or a given speed. So, I mean, these kind of subtle differences will give a very different outcome.
this actually comes down to a problem that is one of control or stabilization. So one could try and ask, can one introduce cars, maybe autonomous cars, in such a way that the traffic is led to a particular configuration, let's say a stable one, or let's say one with certain properties regarding the outflux at the given point. And indeed, there are follow-up studies to that one from the Royal University, in which one asks indeed how many cars does it take in that ring road to stabilize the dynamics. And again, we get into a very vast detail on this topic that driven by concrete, let's say, motivations as exposed in recent years. One can also ask about more general root conditions. So when the flux depends not only on the density, but also on the index. So on some time, let's say, contingencies, and also on the conditions of the street at a particular point. But finally, one can ask about networks. Of course, the circular road is a very special situation, but in our cities, we have other networks, let's say, segments or outlines, in which a relevant question is also what happens at the junctions and how one should dictate the behavior of the junction. And the other is being debated in roundabouts, traffic lights, and so on. So the possibilities for modeling are endless. Although in this talk, I would like to focus on a particular class of traffic models, as announced in the title, that are the non-local ones, which try, in a sense, mitigate the issues with the traffic jams. In the following sense, so what do we mean by non-local? By non-local, in general, we mean that there is some action happening at a distance. In the particular piece of traffic models, what happens is that we suppose that each car looks ahead and adjusts the velocity depending on some average of the density ahead. It's also modelistic simplification in the sense that first cars look mostly ahead, but there is also the back mirror to look a bit behind. But in a first instance, let's say that we focus on the look ahead mechanism. So concretely speaking, in mathematical terms, in the velocity, the density is replaced by rather disaveraged quantity, in which the density is averaged with some kernel gamma, and on some kind of type of space horizon, let's say from the point of the car to the point of x plus alpha, alpha being the look ahead range. Now, intuitively, we should hope that allowing the cars to look ahead should indeed prevent or at least mitigate congestions. This type of modeling consideration, of course, driven by the human nature looking ahead, not only at the single point, but also for some stretch code. But it is even more relevant now with the introduction and popularization of connected and autonomous vehicles. In the sense that, of course, connected vehicles, so-called car, even nowadays may assist or replace drivers, and they use sensors, cameras, connection to the internet, to satellites, and so on, to share data, receive information, and then adjust the behavior, even with information beyond the normal, let's say, stretch road that the human driver may see. And of course, a big incentive for the introduction of these cars is that they should somehow improve road conditions, input efficiencies, input delays, and so on and so forth, input traffic blockages, input traffic waves. But then introducing them requires some kind of modeling behind to actually study their impact. Now, from the mathematical point of view, so then at this moment, we are concerned with two different types of models. The local one, the LWR1, for example, that we discussed beforehand, and this non-local one, in which the difference is the fact that here the car density is based by this average quantity. These non-local models have been studied for quite some time now. Here I cite only the papers, but in fact there is a very large literature. And there are several takeaways that one can have from the analysis. So first of all, there is a better situation with respect to regularity, in the sense that in contrast to the local models, with suitable assumptions at least on the velocities and on the kernel, the same regularity as the initial data is preserved. There is no shock formation in finite time. One can build the solutions with the so-called weight characteristics using a fixed point argument in a way that is not possible for the local problem. Not only that, but the solutions, even the big solutions, are unique. We don't need for an entity distributed criterion to select a unique one. So this is motivated by the fact that the extra, let's say, regularity given by this averaged term prevents loss of information in a sense. Another key property is that the different variation that we had for the local model is preserved in a sense. So mass still moves with different speed. So the car still moves with different speed. Although information moves with different speed, because of course the car instantaneously knows what happens ahead, not just locally, but for a stretch of road. So there are different properties. In a sense, better behavior with respect, for example, to singularity formation. That one may investigate. So just to give a little idea, let's say, of the parameters behind for the construction of the solution, for example. The main point is that if we consider the average, the density, the distance, the velocity as fixed, let's say, a quite regular function of space and time, then this equation becomes linear. And the construction of the solution is classical by following, let's say, the characteristics, by following the part of each particle, let's say. But then, the fixed point argument, one can actually get the solution for the non-local problem, and then show all sorts of nice properties, including the uniqueness without any conditions, the regularity being generated from the data, and so on and so forth. So this part of the construction, and again, I just give a little slide with just a hint of mathematics, but is quite different from the local case, and in a sense closer to the easier linear dynamics. So by linear dynamics, I mean the case where the velocity is just constant. On the other hand, from the point of view of the modeling of the coexistence between, let's say, autonomous vehicles and classical ones, it is important to establish some kind of consistency between the local models and the local ones. That is, one wants to investigate, in some sense, the stability with respect to the local horizon. More specifically, the question is, what happens when alpha, the local horizon, goes to 0? In that case, let's say if we scale the averaging kernel appropriately, this averaging reduces to a point evaluation. And then, at least formally, the equations for the local model reduce exactly to the ones, to the local ones. But then, the question is, to establish this convergence seriously, beyond the formal, let's say, computation, with the objective of reaching this gap between local and local modeling, obtaining some kind of, let's say, stability of the two levels of description. And also mathematically, there is an interest because these non-local models have a bit more regularity than the local ones. And then one can wonder, does this kind of limiting process select the unique entropy solution of the local model instead of a random, let's say, mixed solution. And this topic has been studied quite a lot. Let's say it was first posed as a question in the context of entropy models in 2015, but indeed the local to local limits have a longer history. So let me pose the question a bit more precisely in mathematical terms. We have the alpha conservation law. So the alpha model with the average density here in the velocity. We have our kernel being rescaled with the Nonlocal parameter alpha. When alpha goes to 0, we wish to recover the entropy solution of the local model, of the local conservation law. And here, let me state mathematically what I mean exactly by entropy solution. What I mean is the solution for which every convex entropy is dissipated. That is, I would like this inequality world in the sense of distributions. Just for analytical practices. But more, let's say, freely speaking, what I mean to say is that I want to select out of the local to local limit the unique meaningful solution of the local model to bridge the gap between the two. Just to give you an idea, that with the kernel concentrating to a point, indeed we hope that the dynamics should concentrate to the local one. So there is a long history, as anticipated. Let me collect just a few contributions in a couple of slides, just to give you an idea, but in fact there are many more. This topic really exploded in the past decade or so. And it started, maybe one of the earliest investigations was even from the late 90s, motivated by a different model of a local type, similar to this one, but coming from two dynamics, the so-called non-local Burgers equation, for which one wants to study the convergence to the local one. And in that early study, the standing assumption was that the leading solution should be smooth, which of course is not quite the general situation for conservation laws, as we've seen, because of the formation of shocks. But still, it is an assumption that in some instances it's verified, and it helps quite a lot for establishing the convergence, so then one can do computations by hand much more precision. Similar positive results have been obtained in this question when the initial data is monotone in a suitable manner in such a way to allow for smooth solutions. That also helps a lot. And it also helps to introduce in dynamics a little bit of viscosity, which is an idea that comes from fluid mechanics to consider viscous conservation laws. In that case, the interplay between viscosity and non-locality helps a lot, and indeed one can establish convergence in suitable balancing regimes between the two parameters, the viscous one and the non-local one. So these have been very early positive results. Although in general, there are very counterexamples showing that this convergence from local to local is quite tricky, and in particular, it does not hold generally. So, for example, for physically weird kernels, the convergence does not hold. This was a result from 2019. The physically weird kernels have in the following. For example, in car traffic, where the velocity is decreasing, if the kernel looks only behind, but not ahead, or looks equally ahead and behind, then there are counterexamples to convergence. So this shows that somehow there is a privileged direction of looking, that is, that the drivers should mostly look ahead. This is, again, one of the types of counterexamples that have been put forward. For generally, one can show that there are no bounds on the total variation of density under quite general assumptions on the kernels. So total variation, roughly speaking, measures oscillations in the solution. And to have such bounds helps a lot to get the convergence in the limit as alpha to 0, if the bounds are uniform with respect to alpha, that is. So showing that these bounds do not hold in general, unless there are, let's say, some restrictions. So for example, particular kernels, initial data away from the vacuum, has not been in principle that the convergence does not hold, but puts, let's say, puts us in quite a bit of trouble in the sense that it prevents us from using one of the main tools to get the convergence. However, again, under more suitable assumptions, this type of bounds have been obtained. So, suitable assumptions being car density being bounded from the vacuum. In these occasions, one can also build numerical schemes to simulate the dynamics and then be ready for the implementation. In any case, this situation, let's say up until 2022, shows quite a lot of difficulty in the study of this limit. However, more recently, there have been many positive results. In particular, I want to mention one from 2020-21 by Gresson and Shen, in which they were able to establish, in the particular case of an exponential kernel, so weighting exponentially the car density ahead, by rewriting the system as a system with the relaxation terms, so-called. We're not to get into the details, but it was a very clever idea and allowed them to show bound uniform for the oscillations of the alpha model and then get the convergence, although still assuming the car density to be away from the vacuum, which in principle one would like to avoid. It makes sense, of course, from the theoretical point of view and from the modeling point of view to have stretches abroad without cars. The more general positive results have been obtained from let's say 2022 and forward with a key observation that is the following. A better quantity to study for the sake of the convergence is not the car density itself, but rather the average density. And in fact, for this average density that we call the W in these slides, these bounds on the oscillation that are uniform in alpha hold much more generally. One can prove them, for example, even just for kernels that are monotone, let's say, in the sense that they weight the cards that are closer by more heavily, and convex, which is a bit of an artificial assumption, but still it can be shown to be needed for such oscillation bounds. For kernels that are even more easily visual, so without convexity assumptions, the results are even more recent, in the sense that we obtained it for the first time in collaboration with socio-economic and Fang Wang just this year, using techniques from compressor compactors, which is a tool we have not explained in much detail, but it's a tool that allows from some considerations on the input reduction to gain compactness and convergence for the solutions. And in all these situations, one can also investigate the convergence of numerical schemes to then get, let's say, implementable solutions for mobility. This is just a very broad, let's say, sketch of what's available in the literature, but as I said, it is growing very, very fast. Let me just present a bit, let's say, the key idea in more detail of using the average density as a better quantity for the convergence arguments. So the average quantity is given by the convolution of the density with our integral, with our convolution kernel. So it's an integral term. Now, in the case when the kernel is exponential, we can deduce a very nice ordinary differential equation for this quantity that then allows us to write a different conservation law with a nonlocal source for the average quantity itself, that is this one in the block. Let me not go into the computations about how to deduce it, but I just want to emphasize very briefly that this idea to consider this new quantity leads us to an equation that looks a bit ugly, but in fact it's much more suitable for studying stability properties. And indeed, one can show that this W does satisfy some very nice total variation bounds that then eventually allows us to pass to the limit and get to the local model. This is in the case of exponential kernel in particular, where there is this nice ODE to be used for this argument. But in fact, it can be carried out more generally for more general kernels. One can obtain another equation for W that looks also a bit ugly, but in fact is very, very useful. And also under the assumption that the gamma is convex, one can show it for the in the more general situation, the W alpha enjoys very good stability properties. So the key takeaway is here, as well as in many other kind of non-local models, that sometimes considering the density average helps in many instances, including for the sake of stability. And indeed, in some sense, even from the modeling point of view, it is a better quantity to study in the sense that it gives more global information on the dynamics. Then, of course, one can wonder beyond the convergence also about the convergence rate, and there are results also for that. The convergence rate being driven by the square root of the non-local parameter alpha. So this, let's say, gives quite a complete picture, at least in the case of the convex kernels, for the convergence of WR. And numerical illustrations confirm, let's say, this, in particular, the convergence for various types of initial data. Here I have one shock, one initial shock that leads to a reduction in non-reasonable initial profile. And in all cases, the non-local dynamics goes to the local one as alpha goes to 0. This leaves a question open, though. That is the convergence of the density itself. I mean, it's very nice that the average density converges. What about the actual density? Can one say something? The answer is yes. One can say something, for example, if the kernel is exponential, because out of the ordinary differential equation that we had before, it comes immediately that W and rho alpha have the same limit. But even in more general cases, let's say for convex kernels, one can use a more subtle arguments, using Fourier transforms and suitable frequency splittings to get still the convergence in L2 of the average of the local density to the local one, starting from the convergence of the average quantity. And this is also quite a recent work from 2025. Let me not get into much detail. I just want to give you the key takeaway, that is that at least in the case of convex kernels, the convergence for both W and rho alpha is by now sufficiently understood, not completely, but sufficiently understood. One of the key points that I should emphasize, though, to prove that the limit of this W alpha or rho alpha is the entropy solution is the entropy balance at the non-local level. At the non-local level, the entropy production is made out of three terms. And in particular, let me point out this one in blue, that is kind of a dissipative term. So similar to what happens, for example, in fluid dynamics for viscous perturbations of invisible equations, there is some kind of dissipative mechanism given by the non-locality, at least in suitable situations for the kernel, that helps to select the admissible solution. Not only helps with that, it also helps to go beyond the case of convex kernels, beyond the cases in which one compute perturbation estimates, and to establish the convergence using compensatory compactness theory. So the key takeaway from compensatory compactness is that if one can show that the entropy production is compact in some sense, then this helps to smoothen oscillations in the proximity solutions and get to a limit. And indeed, the dissipative term that appears out of the non-local dynamics helps with this. But once again, let me just condense this into a slide and move forward and not to get too much into the mathematical details. But again, the takeaway being using the entropy reduction and dissipation mechanisms, one can obtain convergence results going beyond convex kernels, going beyond the variation bounds for quite general situations, as illustrated here. So even strictly monotone kernels or just piecewise constant ones. Another point I want to touch concerns the numerical approximations. I was saying before that these are very important for the sake of having really a deployable model that can be used in traffic prediction in real life. And for numerical specializations, a key question, of course, is their convergence, to rigorously the convergence, so that they can be used reliably. And in the case of non-local models, it is important that they should be asymptotically compatible. That is, compatible with the local limit as well. So they should be convergent, but they should also be stable with respect to delta to zero limit. That is to say, we want to study the properties of this kind of diagram. So from the discrete non-local model, we would like to recover both the continuous local model, but also be consistent with the continuous local one. And it is a question that arises in many types of models with perturbation of some kind. In the local case, particularly, this is relevant to account for both local and local dynamics, let's say, in a given rod. And the recent result that we obtained is indeed that we will be able to build a Goldroof type scheme, which is a classical type of numerical scheme for conservation laws, adapted to the local setting, that is convergent, that converges in both alpha, the local parameter, and the mesh size, with convergence rates that are conjectured to be optimal, like this. And with this, basically, one can implement numerical realizations of the local traffic dynamics in a way that, at least from the theoretical point of view, is fully consistent and then ready to be applied in real life. And of course, there is the question, this is the numerical scheme, just in a page for those that are interested in numerical analysis. Then the question, of course, is to speed it up, to make it really suitable for real life implementation. But then we get into a different line of work. The time is almost up, so let me conclude this talk by mentioning some further topics that I did not touch upon in this brief presentation. So the first one is the following. All the current results concern look-ahead non-local effects. In fact, as I mentioned before, there are even some counterexamples when we disturb a bit this look-ahead effect by allowing the cars to look behind in a symmetric way. Still, one could try to combine look-ahead and look-behind effects, which are consistent with human behavior and autonomous cars' behavior, in a suitable balancing regime, in such a way that the resulting model is consistent with the local one. Secondly, one could try to study second-order non-local models, that is, non-local regularizations of systems of conservation models coming up. There is some work already on this topic, but very little compared to the Scala case. So this is quite open and important for a more accurate description that encapsulates, let's say, a broader range of observed phenomena. Third, here we focused on the case of the particular non-local models in which the velocity depends on an average of the density. But in principle, this is not the only way to build a non-local model. One could, for example, consider rather that the cars move with a velocity that is averaged, looking ahead, instead of depending on the average of the densities. So the convolution is outside of the velocity, so they need mathematically. But on this type of models, there is some work, but again, not quite as much as the other type of model that we studied in this talk. So there is much more to be done here, and it is of relevance to describe several types of observed traffic phenomena. One could also incorporate both non-locality in space and non-locality in time. Also is a topic that has been not as much studied as the models in this talk. And then finally, and maybe most relevantly, for the sake of actual, let's say, traffic regulation in the city or in the county, the local dynamics on networks, which technically, from the behavioral point of view, is quite demanding because describing the dynamics of the junction with a look-ahead effect is not straightforward. But again, it's a challenge that is important for the future. And in general, there are many problems here. I don't go into the technicalities, but there are many problems in traffic description that are open, that are mathematically relevant, and that most importantly are challenges for, let's say, actual traffic regulations for our cities. You see, we try, this is a picture of my own town actually. We try in all this to do really applicable mathematics in such a way to allow for a more sustainable urban mobility. So with this, I will finish here, but I'm open for questions, of course, both on the more realistic side, and also on the more technical side if someone wants to ask. Yeah, thanks.
Did you use any?
Thank you. A nice talk. Any questions?
Did you use any traffic simulator for checking your model?
Oh, yes, there is, well, not me personally, but there is quite a lot of work done by actual traffic engineers of trying to match the local dynamics to the actual data. And indeed, I mean, okay, there are, we go back to the very first slide, the mathematical models are wrong, so there are some limitations. But in total, it is surprisingly accurate how the local dynamics reflect the actual, let's say, data collected. This is mostly done in the US, I should say. There are many groups in traffic engineering that are very active on both sides of this issue. So both trying to validate the models from the data and trying to use the model out of the data, so solving the inverse problem, both analytically and also more recently using machine learning techniques.
So, thank you very much. I have a question. I did some game theory stuff way back, and we came across a game that was, it's created some different players at the same time. So are all your traffic, all cars, do they have the same kind of, in this kind of abilities and striving for the same thing? Do you see what I mean? Are they all agents the same?
They have well-tempered drivers and some more rough-speed drivers.
Yes. So if I continue with that, we checked out some psychology literature, and there was a paper that categorized drivers into 3 classes. One was the biggest class was optimal, taking you from A to B as fast as possible, which I think I can adapt to. And that was these competitors that their goal was to beat the other car, no matter what. And then there was a third one, a really rare one, called collaborators, that looked at the whole system and tried to optimize the whole collective, which a friend of mine is in part of. So would that be possible to have different kernels for these types of, and then mix them together? Yeah. Oh, sorry.
I didn't mention it here, but the multi-population models that are studied for at the local level also have been studied more recently with local effects. So in which there are different types of vehicles, or they can also be interpreted as different types of drivers for the vehicles. And in the local models, it is possible to have for each of them a different velocity and or a different curve that averages the density ahead. But the study is much more open there. So there is much more to do.
But do you think you can come up with a kernel that fits with these kind of categories? Would you think, be able to do that, do you think? Would you be able to see a kernel that will fit with these 3 different categories that I talked about?
One can build one log. Both curve and velocity they will account for these 3 types of behavior. And indeed, I mean, there is some work on this line of work, but not as much. I mean, it's of course being a system, the situation is forbidden. But it is a topic of great interest. And looking at the game theory, actually there are several areas, especially regarding dynamics of networks, that use the tools to model the diverse behavior and to model the behavior in particular at the junction. So seeing in which way the traffic density will fit in the junction. So this is also a good point about this topic, that it brings together expertise from different areas. So there are the analysts working on the modeling and on the properties, the numerical people working on the simulation, but also people coming from other disciplines, I mean, engineering, socio-economics, and so on and so forth, to try and come together for, let's say, the objectives of improving mobility.
Thank you.